In this problem, we are doing what's called a geometric related rates problem. So these are interesting problems that have applications to the real world, and you look at how fast one thing is changing in relation to another, or how fast they're both changing in relation to time. So let me show you how this one works. The first thing I think we should do is talk about the scenario so that you kind of have a good basic intuitive understanding of it. The situation is a man who's 1.9 meter tall walks directly towards a light pole at a certain rate, and the pole is 5 meters above the sidewalk, and then a shadow is cast onto the sidewalk, and we want to know how fast is that shadow changing, either growing or getting smaller. So let's think about this first. I'm going to draw a little picture. So we've got a light pole, we've got a guy somewhere in here, and there's the ground. If we think about the light rays hitting the guy, we can turn this into a right triangle. The shadow, this is going to be the part that's the shadow, because that's the part where the man's body is blocking the light of the street lamp. As the man walks closer and closer to the street lamp, sometimes it can be confusing to decide, is that shadow getting longer or shorter? You might think it's getting longer because he would be moving forward, so there'd be more space here. But what really happens is the angle of this triangle changes. So let's put him over here. So here, the angle of the light would come down like that, and only this section, which is shorter than that other section. So as you're walking towards the pole, your shadow gets shorter. If you were right next to the pole, it'd be a very steep angle and there'd be just a tiny little shadow. I mean, try it yourself. Go out and find a street light at night and see what happens to your shadow as you walk toward it. All right, so now that we've got that understanding, let's go ahead and make a good diagram with all the numbers filled in and see if we can make any sense of this. So it says the light pole is 5 meters tall, and the man is 1.9 meters tall. And then we'll try to draw this triangle. And we've got this space here that's the shadow. It also gives us this piece of information that he's walking toward at a rate of 0.7 meters per second. So 0.7 meters per second. And then the question asks, at what rate is the length of the shadow changing when he is 6 meters from the pole? So at this moment where, let's call this X and this Y, these things are going to change as he moves, but at this moment, X equals 6. So I think what I'm going to do here is make a proportion. You might remember from geometry that if we have a right triangle and we cut it with a parallel line, you get two proportional triangles. This little one down here, where the base here is the shadow, and the big one where the base is the shadow plus the distance to the pole. So I could set up a proportion that looks like 5 over x plus y is the same as 1.9 over y. Okay. Now, what we're going to do is just try to solve this for y. So I'm going to cross multiply here. So I'd get 5y equals 1.9x plus 1.9y. I'm going to subtract 1.9 from both sides. I'd get 3.1y equals 1.9x, divide by 3.1. And we get y equals 1.9 divided by 3.1x. Now at this point, we're going to apply our calculus. And what we do here is we take the derivative, but not with respect to x. We really want to know how fast y, so y is our shadow, how fast y is changing with respect to time, not to x. So we're actually going to we're going to derive both of these with respect to t. So the derivative of y with respect to t is just going to be dy dt. And over here, well, x is to the first power, so we'll just keep the constant as it is. And this becomes dx dt. You might be wondering, what good did that actually do us? Well, we have the answer, the value for dx dt already. If we look up here, this length x, we've been told it's changing at a rate of 0.7 meters per second. The man is walking towards the pole at a rate of 0.7 meters per second. This value is going to be negative though, because x is getting smaller as he walks toward the pole. So it's going to be a negative 0.7. And I can just plug that in. So 1.9 times 3 or over 3.1 times negative 0.7. And that now is going to give us dy dt, which is the rate that y is changing with respect to time. And let's see, when I do the calculations on that one, I get dy dt equals negative 0.429. Now, negative 0.429, that would say that y is getting smaller. So the shadow is getting smaller. Does that square with what we know? Well, yeah, because as the guy walks forward, that angle changes and the length of the shadow gets smaller than it was before. So we would put, let's see, we want what to the nearest hundredth? Yeah, nearest hundredth. So we'd put negative 0.43 in here, and the length of the shadow is decreasing. So that is a little bit of work with geometric related rates.